Morning, everyone. Before to announce our first talk today, I'm going to give you another announcement. Is 12 and 15, we have plenary talks from Arthur Ávila and Lourenço Dias, and they are going to talk about on the work of Marcelo Viana. You all are invited to be here. And today, it's my pleasure to introduce Professor Carlangelo Liverani from Università di Roma, Tor Vergata. He's going to talk about sequential billiards and the Lorentz gas.
Okay, so it's a pleasure actually to be here, and it's always nice to be in Rio, and also for this occasion. And actually, I think I met Marcelo a long time ago. I don't remember, but it must have been in the mid '90s, and I mean, he was already rather famous, so I was expecting to meet this kind of senior person, and I was surprised. This just kind of good-looking guy that was rather pleasant to talk to. That was first surprise. And then, after some time, I didn't realize it immediately. I realized that he was actually much younger than me. But, okay, still, yeah. Okay, fine. And now I kind of was surprised to learn that he's already 60. Wow, this is kind of, okay. So a life full of surprise, at least for the simple-minded like me. And it's really a pleasure to, be surprised again in the future. So, all right, so I didn't know exactly what to talk about because, to be honest with you, lately I've been working on problems that I have not been able to make much progress on. So, but I thought that maybe billiard is kind of a subject that may be of interest also for Marcelo. And so let me just say 2 words about the Lorentz gas. The Lorentz gas has a long history. I mean, it comes for the last millennia, essentially. And it is a model that has been developed in order to describe conduction in metal. And the idea is that there are these electrons that move in metal, and they do not interact with each other, which is kind of not very reasonable unless the density is rather low. And so, but by this hypothesis of non-interaction, you have the fact that it's just enough to study one electron, right? And also the idea is that the interaction with the atom is mimicked by an elastic collision, which is, of course, also totally false, but as a first approximation makes some sense. And finally, they move in a periodic lattice, which is also totally false because metal do have defect, but still, as a first approximation, it does make some sense. All right, so this, for example, is an example of a Lorentz gas in which the atoms, which are the obstacle, are in high density. So there is a whole business about low density situation, which I won't talk about because it's treated by some rather different techniques. So in the high density situation, this is the situation. And the high density essentially implies, in this case, that you have finite horizon, meaning that every trajectory that is long enough will collide. And so this is another example which I like a little bit more because it's easier to treat, and I'm kind of lazy, so this is better for me. It's just, again, the same situation, periodic situation. And so this was actually treated first by Sinai and Bunimovic, and the trick was essentially compactification. Since you are in a periodic situation, you can write the position as the cell in which you are plus where you are in the cell, and this allows you to treat, so this is a cell, And when you get out from here, you can imagine that you are entering from there, since the cell over here is exactly the same. And this means that you can imagine that everything happens on a torus. So you are now have that the dynamics is going to be something which is a cocycle, because you will have the variable that tell you where you are. Well, normally it's done in the Poincaré map, but forget about this. This is just something that tells you where you are in the cell, and this tells you what happened in a collision, and it does not depend from the place in which you are in the lattice, and the place in which you are on the lattice is simply updated by some function that tells me where, for example, if I am here, for example, then I will add the vector 1, 0, because I go to the next step. So it's just a cocycle if you look at it from the dynamical system point of view. And OK, that's fine. So it means that you have an additive function on a system that you understand. If you understand very well the billiard system, which is what was done by Sinai and Bunimovic first, but then there are many, many other people that contributed, in particular Lisa Young, then you can get, for example, the central limit theorem for the behavior of the particle in the system. So you have essentially diffusion. It's just a way, actually, as far as I know, it's the first way in which people were able to get a diffusive behavior from a purely deterministic dynamical system. So that's a kind of notable achievement. And, but the problem is that, in general, as I said before, you cannot expect the lattice to be really periodic. And the simplest situation that I can think of is a situation in which these big atoms, somewhat, these big obstacles are still periodic, but the central obstacle is not. And in each cell is in a slightly different situation. Okay? Now, this idea of compactify fails miserably, because, I mean, every cell is different. So what do you do? Well, you can try to do more or less what you did before. Now, typically, mathematics is something worked, you try to copy it, and then you try to see what's wrong with it, right? And so here, as I mentioned, the Poincaré section, so this, for example, is the Poincaré section that you can use. These guys here and the central obstacle. So it means that people call things that Marco Lenci calls these gates. But in any case, I mean, it means that you just look, you are here, and then you have some velocity, you hit there, and this is the next place. So the Poincaré map will be from here to here, position and the direction of velocity to position and the direction of velocity after collision, and so on and so forth. And then you get some map from this set X, which is just the union of this Poincaré section here in bold, and that you want to essentially do the same trick that has been done before. So again, you say, OK, fine. Now I have that the obstacle are, this is the position of the central obstacle is in some set O star, whatever that is. And if you want to look at the configuration, it will be O star to the Z2, because in each place you have to tell me where in hell is the central obstacle. So you have such a space of configuration that tells you where you have put the central obstacles, and then the dynamics, and these are fixed. Right? Once you put them, they are there. They do not move. But still, you have to put them in some way. And then the dynamics is exactly as before. You just say where you are inside the cell. This is the variable x. And you say where you are in the lattice. And that is the variable z. OK? And then this vector here, Ex, is exactly a vector that tells you if you are in the place PW, then you make the jump W, right? So going backward, if you are here, for example, if you are here, for example, then if the point is here, then it will go in the cell upstairs, so you have to sum to the position in the lattice the vector 0, 1. Okay, so that is exactly the same as before. And now you have to say, if you want to talk about the random Lorentz gas, then you have to put a probability distribution on the space of possible obstacle configuration. Okay? So that is what people do when they talk about random Lorentz gas. But what I will talk about today, it is done for each possible obstacle configuration, provided that you keep these finite horizon properties. Okay? And they do not overlap some stupid minimal thing. Okay, and then, you will see at the end why I am just in this situation. And the dynamics is again as before, but now you are in trouble because, okay, the position in the lattice is updated as before. According to where you are, you make a jump, but the dynamics depend on where you are. Okay, and so now it's not a cocycle anymore. Now it's a fully coupled dynamics, and you have to worry about it a little bit. So this is a problem that you look at it and say, okay, I have no idea what to do, but maybe a good question is, what do you want to compute exactly? What is that you're looking for? So the third thing that I would like to compute is a probability of a path. So you tell me, okay, the particle have been in this cell, in this cell, in this cell, and then I want to know what is the probability of seeing this path among all the possible, all the possible paths that could happen. So for this, there is a stupid formula, which is, what's wrong with that? Which is this one. This is simply says that the initial position is distributed according to some, well, here the initial position must be random, but I want the minimal possible randomness. What is the minimal possible randomness? I tell you in which cell I am, but I do not tell you where I am in the cell. Where I am in the cell is given by some probability distribution. That is, if I don't do even that, then I tell you just some initial condition, it will go somewhere. I have no idea. There is no probability. I have no idea what to do. Okay, so that is the formula. It means that at time 0, I was in the place in which I do the right jump. These W are the jumps that I do from one cell to the next. Then at the following time, I evolve with the dynamics that I find in the cell Z1. And then I do the jumps that take me to the cell Z2, and so on and so forth. And then I change variable. Don't ask me because I change variable. It's kind of, I don't know. This is the difference between the Koopman operator and the Rouel-Perron-Frobenius operator. There is no real difference, really, right? At the beginning, I thought there was a difference, but the more time passes, I see that it's the same. It's just a different way of seeing the same thing. They act on difference. One acts on the dual space of the other, but this is like a tradition, right? I don't know. I'm used to use this operator that compose with the inverse, and okay, apologies. So this is just, yep. This is the probability of an itinerary in the cell. When? No. You look at the, okay, so since the lattice of the obstacle is actually fixed, that only the central obstacle changes, then you can imagine that you are on a lattice, right? And so these are the variables z that tell you in which cell you are. Every cell looks like this. And then there is a central obstacle, right? And let's say that the center of the cell is where you are. And then you jump from this cell to this cell, so it is just a walk on Z2. And I don't tell you where I am inside the cell. I tell you which walk I'm doing in Z2, and I want to see the probability of this, given the fact that at the beginning I was distributed inside the cell from which I start in some reasonable way. Is that clear? Okay. So, all right, so you get some funny formula. And of course, you can write it in terms of transfer operator. It's just one way of writing things. And how does this look, this transfer operator? Well, there is, you take, this is a density. You compose with the inverse map. And then you just put the characteristic function, because you know, since I tell you which path you follow in the lattice, then you know at each step the point must be in the place that allow it to jump in the next cell that I specified. So if I know that if the dynamics end in a different place, then it's not a dynamics that realizes this walk in the lattice. Okay, so then essentially you get a transfer operator with a potential. This is a potential, but the potential is a bit nasty because it's 0 somewhere, right? If you look, open a book in transfer operator, normally they write the potential e to the phi. No, it doesn't work because e to the phi is never 0, right? Well, unless phi is minus infinity, which you don't like very much. Okay, so that is the, so you can write, actually, you can use this type of operator to write the probability, okay? So this is just the probability. You can write it as the integral of a composition of this operator. And this leads you to what people call sequential billiard. So you have a dynamical system, not always the same dynamical system. At each time, the dynamical system changes. And then you want to know what happened to a probability distribution when you apply this sequence of dynamical system, which is specified. You have no idea what it is. It's something in some class, of course. Okay, here the class is the class of billiards with some properties. Okay, so now what you want to prove, actually? Well, what I would like to prove is what is called loss of memory. I want to, which is the equivalent of decay of correlation for a single system. So what is loss of memory? Loss of memory, I want to say that in some sense, what happened to the probability distribution doesn't depend from the far past. Okay, but the problem is that, the probability is given by this, some sequence of this transfer operator applied to the initial density. Okay, so that's what I want to study. But the problem is that, you see, if, for example, at the beginning, some mass of the distribution that I'm looking at end up in a hole, I mean, end up in a place in which it should, let's say that is all supported in a set. Imagine that you have, you know, this situation. Okay, and at the beginning, you are here. Let's say your probability distribution is supported here on this set. But the path that I tell you is that from here I go there. The probability is 0, because there is no point in your probability distribution that does that. So it means that if you can lose mass, and if you lose mass, you lose it forever. So it means that this quantity here, if I start from two different guys, that, I mean, in size, there's no reason why it should be equal. It is different, it may be different at the beginning, and it will be different from ever. So if I lost some mass at the beginning, I will never forget it. What I can forget if I normalize it by, you know, the mass that I had up to some previous time. Then I do this, then I can hope that it will go to 0. So this is what I mean by loss of memory. And if you look at it in terms of, from the point of view of a probabilist, then this means that you're looking at conditional probability. You are looking at the probability of seeing certain number of steps from time n minus k plus 1 up to time n, given the fact that you know what happened before. Okay? And you want to say that this quantity here, somewhat, does not depend very much from the first guys here, from what happened at Z1, at Z2, at Z3. That will be loss of memory. This conditional probability depends only from the near past. I mean, ideally, if you have a normal random walk in random environment, then the conditional probability does not depend on the past at all, in the sense that to jump left, right does not depend on where you were in the previous time step. Okay? That is normal random walk in random environment. Here it seems a little bit unrealistic to expect something like that, because system is deterministic after all. So the idea that everything is forgotten in one step is kind of ridiculous. But maybe the best that you can hope is that there will be an exponential decay of memory. So the thing that you can hope is that this limit will go to 0 exponentially fast. Okay, so that is what I would like to prove. And the question is, how do I go about trying to prove that? Well, essentially, I know two strategies that can be used in order to prove this. One is standard pair, and the other one is Hilbert matrix. And we thought a little bit, we worked with Mark Demers on this problem, and after some time, we decided that maybe it was easier to use the second strategy, because standard pair are actually very, very nice, but sometimes when you try to write them down, it gets a bit messy. So, or maybe just because we are not able to do it properly, I don't know, whatever. So, what is this? Let me just remind, in case some people, well, actually, Marcelo knows very well. He wrote even a book about this stuff, but one of these N+1 books. But maybe some people don't know in the audience what it is. So the idea is the following. You have a convex cone, okay? And you consider just a section of it by some transversal sections. Then you get a convex set, okay? And then in this convex set, you can introduce a metric, which is called Hilbert matrix, which is this one. You take 2 points, you just take the line through these 2 points, you take the point at the boundary, and then you compute the cross ratio. And the cross ratio has the nice property that is a projective invariant, so it doesn't matter which transversal you took. You always get the same, okay? So this is a metric in projective space, essentially, right? And, okay, you say this is a kind of bizarre formula. The fact that it's a metric, it can be proved is not so terribly hard once they tell you that it's a metric. The idea that it's a metric, well, maybe you need to have Hilbert to tell you that this works. But once you know that it works, you can check. And so that means that, that's right, what I forgot to tell you. What I forgot to tell you is that, of course, in this metric, this set has infinite diameter. Because if you have a point on the boundary, then one of these guys is 0, and then you get infinity, okay? So this is not compact in this metric, this set. Okay, very well. Now, there is something interesting that you can do. You can introduce an order structure. You can say that f is smaller than g if the difference is in the cone, okay? So this gives you an order structure. And actually, if the space, the vector space in which you are, the vector space in which you are working is Archimedean. So there is some guy that if you multiply by some positive number is bigger than anything, then you can define a norm. The norm is just defined in this way. I mean, you just take the minimum lambda such that this inequality is satisfied. And then this norm is order preserving, meaning that if you have these inequalities, then the norm of G is bigger than the norm of C. Essentially, it's trivial from the definition, okay? And so that means that you are essentially in a Banach lattice. So then not only you are in the Banach lattice, but if your operator preserves the cone, okay, if you have the property that your operator preserves the cone, so then this is a positive operator in the sense that if you have a function that is positive in this order, then when you apply the operator, you get another function that is positive in this order. So essentially, you are like in the same situation, although it's glorified, the same situation of Perron-Frobenius theorem for positive matrix, right? When all the matrix, you have a matrix with all positive entries, the cone is just the positive octant in which all the vectors have positive entries, and this is preserved, of course, by the positive matrix, and then it's essentially the same theory. So what you need is some kind of glorification of Perron-Frobenius theorem. That is, in order to apply this strategy. And this is done by Birkhoff, Garrett, the son of George, whatever. But that is the theorem that essentially tells you that if you have that the diameter of the image of the cone is finite, so this is the diameter, you take two guys and in the image of the cone, and then you take the sup of the distance. This is just the diameter of the image. If the diameter of the image is fine, then you have a contraction in this metric, because the hyperbolic tangent is always smaller than 1. So essentially, you get contraction in this Hilbert matrix once the cone goes strictly inside. So if you want to think about positive matrices, this is like saying that the matrix has all strictly positive entries, then it put the positive octant in strictly inside the positive octant, and then you get that there is a unique eigenvector and so on and so forth. You get contraction, the cone squeezes. But it's kind of interesting that it's a little bit better than normal Perron-Frobenius because it gives you an estimate of the spectral gap, so of the distance between the first eigenvalue and the second, which normally is not such a bad estimate. I mean, it's not optimal, far from optimal, but it's not such a bad estimate. So that could be, it's a quantitative version that could be useful in other situations. And of course, you can be a little bit upset because you say, oh, fine, but who cares? This is a contraction in the Hilbert metric. I want contraction in some norms that I can use, that I can do something with, right? And the way of making this connection is the following. I mean, there is a general way to, some general theorem that you can apply to make the connection, but in the case that I am discussing, the connection is given by this fact that if you take two functions that have the same average, so for example, two probability distributions, then you have that their distance in C1 prime. So this means that you integrate, this is the topology of distribution. So it means that you integrate f minus g, and you take the sup on the phi that have C1 norm less or equal than 1. Okay, so in this sense, you control the distance between these two guys, and this is controlled by some constant that depend on the norm of f and g, time the difference between the distance of f and g and 1. So if this guy, if you iterate, apply the transfer operator here, if this is L of, let's say that you have just one operator, so you have L, N, F, L, and G. If this distance goes exponentially fast to 0, then this goes exponentially fast to 0. And so you have that, you get that the function f and g tend to the same object. So that is kind of the abstract theory that I want to use. And in order to use, what I need, of course, is a cone. Okay? So how do I do a cone for billiard? Actually, how do we do a cone for billiard? So this is a bit technical, but I can try to tell you what is the basic idea. The basic idea is that you take stable manifold. So these are manifolds that of points that have the same history in the past. Okay? So you take the set of stable manifolds that are this length delta. And then on each stable manifold, you can take a class of densities.
So the stable manifolds have the same future.
Sorry, yeah, you are right. I have, yep. No, these are stable manifolds, yes, so they have the same future. Apologies. Yes, we are looking for the future, but I am a very confused human being. Sometimes I make mistakes. Yeah, sorry. So the point is that so you have a manifold and you have a density. Well, I wrote it so I can point it to it. And what you look at is the integral of the function that you are interested in on the manifold with respect to this density. There are some class of density, which are kind of smooth, regular densities. And so you can imagine that now you get a new function that is a function that is in a new space. It depends from which manifold you are looking at and which density you are looking at. And this function, you want it to be kind of nice. So you want it to be positive if the manifold is not too short. It should not, oh, sorry. it should not be too large, this function, if the manifold is very short, and it should be older in the sense that if you change a little bit the manifold, you change a little bit the density, then the integral should change very little. Okay? So then you have to introduce some kind of metric on this space. It's a bit technical, but that's more or less what the idea is. So you have more, formula. If you want to see an horrible formula, here is an horrible formula. Okay, okay. So, actually, we are rather happy about this formula, which is true, that looks horrible, but it is 1/3 of the original one. So our original cone had 3 times more condition, and after some time we managed to boil it down to this thing that essentially is what I said. I mean, so this is a little bit stronger. It says that the soup of all these integrals is smaller than something and the inf. In particular, it means that the inf is positive. So this means that all these integrals on pieces of stable manifold are indeed positive. And this one says that, so this one says that if the manifold is very small, then this cannot be too big, okay? Because these are phi are probability distribution. So if they are concentrated on something very small, if the W is very small, phi is kind of large. So it's of order of 1 over the size of the manifold. So that is, you could expect this integral, well, it depends. If f can be very large somewhere, then this integral can be rather large. And this gives you a bound on how large it can be. And this last condition is essentially says that if W and phi and W1 and phi1 and W2 and phi2 are kind of close in some sense, then the integral of this set is close by the distance of this manifold, some power gamma. So there's some older continuity in this invented space. Okay, so this is some cone. It is a bit painful to check that, in fact, this has an image that is contracted, but that is what we prove. We prove that if you take just one, here for simplicity I just wrote it for just one map and one hole, but if you have nearby maps and nearby holes, it's the same result. And they say that there is an n star, okay, such that if you take a power that is large enough, then this is strictly positive. So this is the equivalent to say that you have a matrix that have all entries that are bigger or equal than 0, but there is some power that has the entries that are all strictly positive. And so then you can apply Perron-Frobenius to these powers. That is essentially what we put. It's very annoying that there is this n star, though, because it means that you have to have a certain number of iterations of maps that are very close. Then after that, you can take a completely different map. There is no problem, because it will contract again. But for a while, it should be something that it is close. And so it cannot be applied directly to the model that we had in mind, which is this random Lorentz gas. So what do you do in this case? You have a theorem. It does not apply immediately to your model, so you change the model, right? I mean, so that's what we did. Well, I mean, of course, you should prove a new theorem, but it's much harder. It's much easier to change the model. So we introduce this, what we call lazy Lorentz gas. So that actually the name comes from Dima, that, I don't know, he gave this name to this model. And the model is the following, that if you are in a cell, so this is a cell, essentially you enter in a cell here, and then when you enter this, which we call gate, they shut down. So now these are reflecting. So you move here, you bounce, and now you bounce. And it goes like that until you add a certain number of collisions, which is that n star. And when you reach n star, they open again. At that point, you can change place, right? So this is just, is a place that is a bit sticky. You enter in there, and you cannot get out for a while. Right? There are countries that are like that. So, but anyhow, I mean, so that is the model, which we call it lazy Lorentz gas. And for this model, it works because for you have n star iteration in which you have always the same map that acts. Yeah. Okay. That is absolutely true, but the problem is that there is always some idiotic trajectories that enter and exit immediately, right? Yeah, well, yeah, what about this? I don't know, I mean, it's complicated. Yeah, I mean, okay, I am absolutely agreeing with you. The problem is that if you want to do better, then you have to analyze the combinatorics of the collision. This is unpleasant business. So probably it can be done, but it's an unpleasant business. And it's something that we would like to do, but we haven't looked at it yet. So you see here, the problem was that it was not obvious that one could apply this strategy of finding a cone, because it's a little bit different from previous, I mean, for studying billiard, normally there are this Lysaght tower, then there are these anisotropic Banach spaces by Demers and Zhang, but cones were not really ever used. So it was not obvious a priori that one could implement it. So that's our first step. Then I agree with you, there is much to do. Yeah. Okay. So that means that we are able to prove this theorem, and the theorem says that I mean, you can find some proper cone of distribution, and if your initial distribution is in this cone, for example, it is a C1 distribution, that will be okay. Then you can look at the probability. You give me the past. So these are the jump, right? So the W are which jump did you do? You went to position Z n in the lattice to position Zn plus 1 in the lattice. And the difference is called Wn, or Wn11, minus 1, I don't know, whatever. And so this is the history of the trajectory on the lattice. And then I want to know, given this history, what is the probability of doing a certain jump, or going on the left, for example. And then I have the same probability, but now I know only up to n minus m step in the past. So I know a part of the past, but not all the past. And what I want to show that it doesn't matter. Essentially, the difference between this guy and this guy is exponentially small. So that means that this model is a model that you can look at it as a model that is purely probabilistic. Forget about billiard, forget about dynamics. This now is equivalent to a purely probabilistic model. Is a random walk in random environment where the transition probability depend on the past, but depend on the past only exponentially little. So the memory of the past decay exponentially. Okay, so now you can say, that's very good. Now it's a problem just for probabilists. I go to probabilists and I ask them, okay, so how do I do that? And they tell you, no, this is very hard. Okay. Okay, fine. Okay, so then actually there are some results if you know one step in the past in one dimension. So you need a tube. You can do this model essentially one-dimensional, right? So it would look like this. This is a cylinder, and then you have these obstacles. And then you have the central obstacle. And then it's just the Z now. Now for Z, random walk in random environment is better understood. But yet, the only result that I know is a result of thought, I think, that would apply if the memory was one step. So the transition probability depends from one step in the past. And you look at the proof and you say, okay, now I just fiddle with the proof and I make it work for 2 steps. No, I don't know how to do it. So, okay, so fine. But at least what the achievement is that you take a problem that has two difficulties. One is the dynamical difficulty, the other one is the probabilistic difficulty. Dynamical difficulty is kind of washed away, and you are left with the probabilistic difficulty that is still there, waiting to be solved. Okay, so, well, I would say that I can stop here. Thanks a lot.
Okay. Thank you.
I'm not asking for exact theorems, but rather for philosophy and intuition. So there might be approach to study this kind of billiard in the following way. You first take a window which is, for example, 10 by 10, then you choose random, you make your obstacles move randomly, and then you repeat it periodically. And then you make a window 100 by 100.
Okay.
You make them somehow distribute randomly, and then you repeat periodically. Do you expect that this kind of sequence of billiards would approximate well the random billiard or not? On the one hand, they are supposed to forget the memory fast, but on the other hand, well, one has to be careful with periodic billiards.
So I don't know.
Which would win?
Yeah, because I am uncertain, because the problem is that once you go to a bigger periodicity, then you have to study this new problem. It has a bigger periodicity. So it's true that maybe you have some understanding on the smaller block. So this is what you are saying is something that smells of renormalization, right? I mean, that is more or less. And in fact, that's what, for example, Brickman and Kupianen do more or less for random walk in random environments. They do renormalization and try to do something like that. Maybe, but honestly, I do not know. I do not know.
So I wonder if you can do maybe a simpler situation to be without the need of the lazy stuff, is makes like localized perturbation. I wonder if this is easier. Like you make the exponential, the perturbation decays exponentially with the position or something like that.
So, okay, fine. The problem is that what I want, in principle, is the translation invariant situation. And then, of course, you cannot do anything localized. If you do something strictly localized, then there are results by Dolgopiat and other people in which, in fact, things are okay. But the logic is more or less that you have changed the lattice in some local place. Eventually, you get out of this is ergodic. If you do not get out, it's some ergodic billiard, right? Eventually, you get out. When you get out, you are in the periodic. So you have just to compute what is the probability of going back to this region, and then it's kind of, but essentially you are just saying that you stay most of the time in the periodic situation. So if you try to put an exponential decay of, maybe something can be done again, but it's not what people normally, I mean, because the motivation comes from, a piece of material. Yeah? So there's no particular reason why the defects that you have here are different from the defects that you have there. Right?
And you're not moving modifying the shape of the obstacles. So if you make like is asking too much to have a similar things with like one parameter family of perturbations of the circle and ask similar questions? Or?
No, then you can, I don't change the shape again because, again, laziness. I'm a very lazy person, but you can. There is a small problem, a technical problem, if you change the length of the boundary, then the Poincaré section change from one to the next, right? And then you have to make sure that the map is hyperbolic. And this is a bit maybe annoying if you change things too much. But while if it is the same, then you know already that the map is hyperbolic. And we try to take away all the difficulty in order to have the most simple situation. But yeah, this can be done.
I did not understand about the stable manifolds. How do you compare two different stable manifolds? They are in a kind of stack because of the school product.
No. It's just we declare that we have two stable manifolds.
Okay.
Okay, and there is some approximate unstable direction, and let's say, so we just fix some approximate unstable direction, and then you can go along this unstable direction, and then we say that the manifolds are closed if this distance is small and this mismatch is small. That is just very naive way of saying that two things are close. I mean, they must be physically closed, and if you unite them by something that is more or less in the unstable direction, the mismatch should be small.
So you can't compare manifolds that are just like this?
No, these are infinite distance. Yes, these two manifolds are at an infinite distance. Yes. But the point is that when you iterate, they spread all over the place, so you can always find pieces that you can compare.
So I have a stupid question. So when Lorentz proposed this model, he thought it's too difficult, and Ehrenfest did this discrete simplification where you randomly put 45 degrees obstacles on square lattice, and then do you think anything could be applied there?
I honestly do not. I think it's a very different problem, because here everything that I do is based on hyperbolicity, on the fact that the obstacle is not flat. If it is flat, then it's kind of very difficult, very different situation. So I doubt that you get. I don't see any reason why you should forget the past.
But
in the same
numerically,
way.
the behavior is the same for the two models. That physicist did.
That is quite possible, but I don't know. Yeah.
Thanks.
So I was in the room when Sinai first presented this result, his results in December '79, I guess. And there were several physicists in the room, and they were a bit shocked because before the rigorous treatment by Sinai, there were perturbative type of treatments, and there were two differences. One is not so important apparently, is the fact that it was Sinai looked at the periodic case instead of the random case, contrary to what was done after Lorentz. But the main shock was the fact that he had sub-exponential decay of correlation, while people who were doing approximate treatment were having exponential decay. But there was a big difference. The sub-exponential decay was by counting having a discrete time, while the perturbative system were with a continuous time, the real time. So at that, many physicists immediately raised their hands and asked Sinai whether or not if this made a difference, and he could not answer for good at that time. I don't know if you know about whether or not this problem of time, continuous time versus discrete time has been resolved. That
Yes.
was already a long time ago. So.
No, not long time ago. So first of all, it is true that the original estimate was sub-exponential by Sinai and Bunimovic. There is a further paper by Sinai, Bunimovic, and Chernov in which it was still sub-exponential, but for the discrete time. But then Lisa-Yang proved that it was in fact exponential, also for the discrete time. There were many at the time, I remember, I was around, so I remember there were many papers that were making numerical simulation, and they were trying to compute what was like, so they were saying, okay, the decay of correlation is e to the minus alpha t to the gamma, and what is gamma? So that was the question, right? And then there were papers, is 0.4, is 0.5, and stuff like that. And actually, Lysang showed that is 1, okay, fine. Actually, there were even papers after Lysang paper that claimed that it was something else, but forget it. But in any case, but that is for the discrete time. For the continuous time, actually, it is exponential also, but that is a much more recent result, actually by myself, Mark Demmer, and Vivian Baladi, in which we proved that for the exponential decay of correlation for billiard in continuous time, it is in fact exponential also. So everything is exponential. That is the end of the story for the moment. Well, no, I exaggerate, right? Because you can have things like this. Okay, then it's there are open problems if you have cusps and stuff like that. But, okay.
Two questions. So what happens if you have periodicity only in one direction?
Yes.
And the second one, are there any results in 3 dimensions?
Okay, so these are two very different questions. I mean, in the first question, well, the answer is actually the same. I don't know. I mean, but so if you are honestly, I am not sure. I'm not sure how to take advantage of the fact that I have periodicity all in one direction. The reason is because already in the case of a tube, I don't know how to prove CLT. So this is periodicity only in one direction, right? Because the other one, you can imagine that is periodized, right? So that's it's already a problem there. If I would be able to prove something for this model, which corresponds to your situation in principle, I would be very happy, but I'm not. As far as higher dimension, the problem is that there is a technical problem, which is that we don't know how to prove decay of correlation in higher dimension for billiards. So this is an open problem. It's extremely annoying. But yeah, because it's extremely annoying because we happen to live in 3 dimensions, right? If we were in flatland, it would be okay. But for us, it's bad. But as far as I know, there are no real results on that. I mean, there are some conditional results.
But do you expect the decay of correlation?
No, I expect. Look, I mean, I am a little bit reluctant to say. I did a conjecture once in my life. Once. It was disproved at the end of the talk. So I am reluctant to make conjecture. I have been burned once already.
Okay. Any more questions or comments? If not, let's thank Liverani again. We return in 13 minutes.